Today we're starting with creating new functions from old. Math 12, we would have called this unit transformations. So I just want to remind you of what we did in Math 12. Started with a function y equals f at x. And if we had a point on the graph of that function, the ordered pair xy, or x, f at x. So we took this function y equals f at x and we transformed it. So here are all the transformations we learned how to do in Math 12. We could put an a in front, which would give us a vertical expansion or compression, and it was composed, operating or multiplying the function f, and this here inside of the square brackets is a composition, b bracket x minus c, close all your brackets, plus d. And then remember that outside the function, the a and the d are going to affect the y component, that is the vertical component of your graph. The a and the d. The d will shift it up or down, and the a will expand if it's bigger than 1, or compress if it's a proper fraction, and reflect it if it's negative. Inside the function, the b and the c are going to affect the x values, that is the horizontal component of your graph. And similarly, the c is going to shift it left or right. So the c will shift it left or right, and the b will expand it either horizontally. If the b is bigger than 1, it will compress it. And if the b is a proper fraction, it will expand it. By which I mean, if the b is 2, it's compressed by half. If the b is a half, it's expanded by 2. Remember taking the reciprocal of all those. Okay, so let me write down for you what the mapping was for the point xy. So if we transformed the function algebraically, then the graph transformed like this. Sorry, I need to erase to give myself some room here. Come on, eraser. A new technology that I still need to learn again. So here is my transformation then on my mapping. So it became 1 over b times x plus c. So that b, we took the reciprocal. The c, we changed the sign. So that's what happens to the horizontal component. The vertical component just is what it is. A times y plus d. So that allowed us to transform graphs. So for example, just getting you started here, if you had a function like y is equal to x squared, then you all know that that's just a basic parabola with a vertex at 0, 0. And if I said y is equal to x squared plus 6, that you moved it 6 up. And it still looks exactly the same, but now the vertex is at 0, 6. And if I said it was y is equal to x squared minus 5, you would remember that that was 5 down. And of course, if you wanted to move it to the right, you would have to write this, x minus 6 all squared. Remember, so this would move it 6 to the right. So remember, to move it to the right, you do the opposite sign. To move it down, you do exactly what you said you were going to do. Alrighty, then let's have a look back at our note. So here are our summary of our translations. Y equals f at x plus c is showing me that this is going to shift c units up. The plus c is outside the function. You want to move it down, put a negative in front. If you want to shift something horizontally, you must compose that function. So to move its c to the right, it's the function acting on x minus c. If you want to shift it left, the function acts on x plus c. But that is a composition. So let's graph these functions here. So I'm going to graph root x. So it goes through the point 0, 0, 1, 1. And make this easy for myself. If x is 1, 2, 3, 4, then y would be 2. And if x is 9, oh my. If x is 9, then y would be 3. And so here is my graph. One, 2, 3, 4, 1, 2, and 5, 6, 7, 8, 9, 3. So there's my graph for root x. If I want to graph g of x, which is root x plus 2, everything is going to shift 2 up. So this point here at 0, 0 will be the point 0, 2. This point 1, 1 will be the point 1, 3. This point where x is 4, y is 2 will be the point x is 4, y is 4, because we're just moving everything 4 up. And last of all, if I'm looking at h at x, root x minus 3 minus 1, the minus 1 is going to move it 1 down, but the minus 3 composed inside the function is going to move it 3 to the right. So my function root x is going to move 1 down and 1, 2, 3 to the right. This point 1, 1, 1 down and 1, 2, 3 to the right. This point 2, 4, move it 1 down and 1, 2, 3 to the right. And there is that transformed function. So that's how you shift it, both vertically and horizontally. What about reflections? Okay, so when we're reflecting, we're changing signs. When we change the sign in x, we reflect over the y-axis. When we change the sign in front of the function, we reflect over the x-axis. So recall that this y equals negative f at x is the same as saying negative y equals f at x. And then you would multiply both sides by the negative. That's why we often say you changed the sign on the y, you reflect it in the x-axis. Last of all, we have what we call an inverse, and that is when you exchange x and y, you get the inverse. I know what I also said in Math 12. I also expressed a reflection in the y-axis. When we flip something, change the sign on x, and you flip it over the y-axis, it will look backwards. Okay, so when the negative is in front of the x, you're reflecting in the y-axis, it looks backwards. When the negative is in front of the y, you are reflecting in the x-axis, and it will look upside down. Okay, let's remember our exponential function. Y is equal to 2 to the power of x. And let's just graph it. So I'd like you to think the t-chart in your head. If x is 0, 2 to the 0 is 1. If x is 1, 2 to the power of 1 is 2. If x is 2, I've got 2 to the power of 2, which would be 4. And if x is 3, 2 to the power of 3 would give me 8. And I'm already off the graph. If x is negative 1, I would get 2 to the negative 1 is a half, 2 to the negative 2 is a quarter. And so you can see that I have this horizontal asymptote along the x-axis. Okay, so there's my function 2 to the x. So let me label it. Okay, if I graph 2 to the minus x, I'm changing the sign on the x. I'm reflecting it over the y-axis. It's going to look backwards. So let me just choose a different color here. If I have 2 to the minus x, then it's going to look backwards. So anything on the y-axis will stay on the y-axis. The point x is 1, y is 2 will flip over to the other side. The point x is 2, y is 4 will flip over to the other side. And this point here, x is negative 1, y is a half, flips over to the right-hand side. And we've got our exponential function coming this way. So, of course, you remember from exponent laws, if I have 2 to the minus x, it means I have 1 over 2 to the power of x, which should be why the blue graph looks like exponential growth and the red graph looks like exponential decay. Okay, what about if I graph negative 2 to the x? Well, now I'm graphing a reflection in the x-axis. So I'm going to take this blue graph and I'm going to flip it upside down. So this point x is 0, y is 1 becomes x is 0, y is negative 1. This point x is 1, y is 2 become x is 1, y is negative 2. And similarly, the 4 will become a negative 4. The 1/2, a negative 1/2. And I think you can see what happens here. We've reflected it upside down across the x-axis because we changed the sign on the y. Last but not least, let's graph j of x is log to the base 2 of x. Okay, so just so you remember that this is an inverse of my original function. How come what justifies me calling it an inverse? So let me give you a little proof of this. So in order to find an inverse, recall that we take every x value and make it a y value. Every y value turns into an x value. So if I start with my original function there, f at x equals 2 to the x. I'm going to write it this way. Y is equal to 2 to the x. If I'm finding an inverse, I'm going to exchange x and y. And when I'm finding an inverse, exchanging x and y is just the first step. To complete this process, we need to solve this for y. And so what I'm going to do is take this from exponent form to log form. You remember this? Okay, so that means that if I take and I write x equals 2 to the y in log form, I have log to the base 2 of x is equal to y. So that's why I'm saying log to the base 2 of x, j of x is the inverse of f at x, 2 to the x. So what does an inverse do? An inverse reflects it over the line y equals x. That is, it's reflecting it across this line. So take that red graph and reflect it across that line, and this is what you're going to get. You're going to get the horizontal asymptote will become the vertical asymptote, the y-intercept will become the x-intercept. You're going to get that function. That is your log to the base 2 of x. Okay, over the page, we've got stretching and compressing. So, when I have a c or a b value, oh, this is all c's. So, y equals c times f at x. Stretch vertically by a factor of c. Y equals 1 over c times f at x. I'm compressing vertically by a factor of 1 over c. If I want to compress it horizontally by a factor of 1 over c, I multiply the x by the c, and if I want to make it larger, I multiply it by 1 over c. Let me put some numbers in here because I think you will understand it way better if I write it like this. So, that is, if I have y equals 2 times f at x, you've got a vertical expansion by a factor of 2. If I write y equals 1/3 times f at x, you have a vertical compression by a factor of 1/3. Then, if you write, I need space, that's why I'm doing this. I will figure out the eraser better for the next time I teach on this, okay? Good enough. Okay, so then if I write y equals the function at 2x, then inside the function I have a horizontal compression of 1/2. And if I write y equals the function at 2/3 x, I have a horizontal expansion by a factor of 3/2. So 1.5 times bigger. All right, so those are your stretch factors. I would like you to remind yourself how to graph a sine function. So this is something I expect all of you to be able to do. Let's set up our scale the same. Call that 1 and this -1. And then let's call this pi by 2, pi, 3 pi by 2, and 4 pi by 2, or 2 pi. Then, of course, negative pi by 2, and you can go backwards. All right, so my sine function starts at the center, rotates up to the top, back to the center, to its minimum, and back to the center. And here is one cycle of a sine graph. Take it backwards in the other direction. And there we go. So there's our sine function. And if I were to graph y equals the sine of 2x, then I'm going to get a horizontal compression by a factor of 1/2. That is, I'm going to take and make this sine function horizontally narrower. So it will no longer have a period of 2 pi. It will only have a period of 1 pi. So between 0 and pi, I have to get that whole shape going. So let me graph that. So it's going to start here and end at pi. So compressing it horizontally, it's not going to take pi by 2 to reach its max. It's going to take pi by 4. And it's going to be back down at the axis at pi by 2 and at 3 pi by 4. So it would horizontally compress. It would, and let me do 2 cycles of it. Okay? So there's a horizontal compression by a factor of 2. If I'm graphing 3 sine x, that will be a vertical expansion by a factor of 3. That is going to affect the height, the amplitude of this, if you will. So instead of 1, it would have a height of 3. Instead of -1, it would have a negative height, go down to -3. So my sine graph, 3 sine x, would look like that. Okay, you can try 1/2 sine x on your own. It's just going to get really messy if I graph another thing on there. It's just going to have half the height. So this was a vertical expansion of 3. 1/2 would be a vertical compression of 1/2. And then it would just be in between here, -1/2, +1/2, and -1/2. All right.